Hi there, I'm Zack Slepian at University of Florida, and today I'm going to tell you about work done in collaboration with Jamin Hu, also at UF and also at this workshop, and Michael Bartlett at Oklahoma University. So my talk is about the odd CMB, and I hope provocatively titled it Odd CMB Out. CMB four-point function is insensitive to large-scale structure parity violation on few hundred megaparsec scales. So I hope the first part of the title is provocative and the second part is precise, because I want to be very careful in this talk about what I'm claiming and what I'm not claiming, and you'll see why all of the words in the second part of this title matter. So, lightning review of previous work. Parity violation seems to have been found in the four-point correlation function of BOSS. Recent work by my group at UF seems to see 7 sigma evidence in BOSS CMAS and 3 sigma in the much smaller low Z sample. Oliver Philcox also has some recent work, also seeming to find 3 sigma in CMAS, and his work is consistent with ours if the same analysis choices are made. This data work is reported in the Hu Slepian Con paper linked at the very bottom of the slide, and you can also see the talk by Jamin and the roundtable with Oliver and Jamin and myself and a few others. And this is all based on an idea of Con, Slepian, and Hu in a PRL to search for parity violation with the four-point function. The idea is simple, and it's shown at left. You have 2 tetrahedra, they're mirror images of each other, and we simply go into the universe and ask, is there an excess of tetrahedra over their mirror image? If so, that's parity violation. So on the lower right, I'm just showing you the kind of money plot from the four-point function data paper by my group, where it's showing you that the black/gray histogram is quite a bit to the left of the orange data line, and the vertical data line is where our data falls, and it's 7.1 sigma away from the center of that gray histogram in units of the histogram's width. So the question we may now ask is, would we expect to see this parity violation in the CMB? So the idea is if there's a real odd four-point function, it is indeed primordial in origin, so it should be there before the CMB forms. So you might think you could see it. So should we see it in the CMB? Well, recent work by Oliver, again, see the roundtable and also his talk, argues that we should see it, but that we don't, and therefore that the BOSS detection is false. So I've highlighted the relevant part of his abstract here. He writes, our results also indicate that the recent parity excesses seen in the BOSS galaxy survey are not primordial in origin, given that the CMB dataset, etc. So he's saying we should see this in the CMB, we don't see it, and therefore it rules out the BOSS results as being primordial. In this talk, I will argue that this point of view is probably not correct, and that parity violation on the scales observed in BOSS would not be visible in the CMB. So first we need a little not cosmic microwave background. So step 1 is we measure the 3D large-scale structure four-point function in a rotation invariant basis. This we call the isotropic basis. It puts one galaxy at the origin, and then the other 3 are pointed to by unit vectors. This basis is complete, it's orthogonal, and critically it splits into even and odd parity modes. This basis was developed by me and my colleague Bob Kahn in a Journal of Physics A paper and on the archive there. So second point is odd parity modes. All of the odd parity modes are proportional to the scalar triple product R1 dot R2 cross R3. This is evaluated at a given vertex of the tetrahedron, and then we eventually cycle over all vertices. Now, we can give R1, R2, R3 unique identities by saying that R1 is less than R2, less than R3, and without this, the basis is overcomplete. So we can now ask, can we have 3D parity on a flat 2D subspace? Now, 3D parity takes x, y, z to minus x, minus y, minus z. On our 2D subspace, we'll only see x, y going to negative x, negative y. Now let us suppose we apply a rotation about the z-axis of minus 180 degrees. This will take minus x, minus y back to x and y, so it undoes the parity flip. This means that we can't see parity in any 2D subspace if we're averaging over 3D rotations, because we'd integrate over rotations, including the one about z that I just mentioned, we wouldn't see anything. So this means that rotation invariant or isotropic 3D physics cannot produce a 2D parity odd signature. In particular, isotropic yet parity odd inflation models won't. So we can then ask, is the CMB really a 2D observable? Well, kind of, but not exactly. So it is a spherical shell, and we're observing it from the inside at the center. So this reminded me of a great poem by Günter Grass, In the Egg, or Im Ei in German. It says, we live in the egg, we have covered the inside wall of the shell, we are being hatched. Whoever is hatching us is hatching our pencils as well. set free from the egg one day. At once we shall make an image of whoever is hatching us. And indeed, this is the goal of CMB cosmologists. We're living inside the cosmic egg, and we want to figure out what the universe actually did at the beginning, so to speak. Who's hatching us? So if you've ever peeled an orange, you know that it can't be embedded in a flat 2D space. Same goes for the CMB. So this is just another way to view this issue. These are just on the right lower map projections of Greenland, and you can see the size of Greenland varies wildly when you go from Mercator to Plat Carré to Spillhouse to other map projections, and this is because you can't really map a 2D spherical shell to a flat 2D surface. However, Earth was believed to be flat until the 1500s or later, although apparently there's some debate about this, and people as early as Pliny the Elder in 77 BC pointed out that it wasn't flat and that was common knowledge. But in any case, I think this idea of the Earth's being flat is a good metaphor. By the way, this is the first map that used the word America. This is the Waldseemüller map from 1508. And the reason people may have thought, and some may even still think, that the Earth is flat is because the length scales we observe are generally much less than the radius of curvature. So we live, so to speak, in the tangent plane, very close to the point of tangency to where we are on the Earth's surface. So this argues that for the CMB, you're going to need scales of the order of d star, the radius of the CMB sphere, to see that it's not flat. So d star, the distance to recombination, is about 15,000 megaparsecs. Now in BOSS, we probed scales from 20 up to a few hundred megaparsecs. These are much, much smaller than d star. So with the analogy of Earth in mind, it seems unlikely you would see parity violation in the CMB, even if it's there in LSS. But let us hatch our pencils and do a calculation to see quantitatively whether this is true. So the setup is that we imagine we can sit in the universe at redshift roughly 1100, imagine instantaneous recombination. In reality, it has a width of delta z of about 100, which is still much less than 15,000 megaparsecs if you convert to a distance that's of order 100. And today, we're then seeing photons come to us from a spherical shell that slices through the matter density at z star, and the shell will have radius of exactly the co-moving distance from us to z star. This shell is increasing with time. We get to see photons coming from concentric growing spherical shells, but that doesn't matter because our time scale is much, much shorter than that time scale. So before takeoff, also fasten your seatbelts and recall our basis functions. The 3-argument isotropic basis function, P, L1, L2, L3, is proportional to 3 spherical harmonics. The 4-argument one, given at the bottom here, is proportional to 4 spherical harmonics, and it also has an intermediate angular momentum, L01 here. So now, on the left, I've written the CMB temperature fluctuations, delta T. We can take those at 4 absolute coordinates where x0, x1, x2, x3 go from us to the CMB, and we can expand that in the isotropic basis of 4 arguments with expansion coefficients capital T. All of the distances are just d star, the distance to recombination. We can also expand the 3D parity odd 4-point function, zeta, in the 3-argument basis functions. That expansion is given in the second line here, and I've written it using r's, and the r's are related to the x's by xi equals x0 plus ri. So we're starting at x0, and we're taking 3 relative positions on the right-hand side of the second expansion. Now, the CMB T coefficient that we want is just going to be picked out by orthogonality. We just integrate P star of 4 arguments against the 4 delta T's and subject to the constraint that we're on a shell. So that's where the delta functions are coming from. Now we can also observe that the CMB temperature fluctuations will be proportional to the density fluctuations on that shell. So we have the 4 delta T's are proportional to zeta. So plugging in our expansion for zeta in the 3-argument basis functions, we get this equation. Our T coefficient of the CMB is some integral over the 3-argument basis function expansion of the large-scale structure 4-point function in the first line, the zeta, and then times the 4-argument P star and the delta functions. So we now have, and I've just reproduced the equation from the previous slide, we now have a problem that actually takes the structure of a convolution. So the second block here is just rewriting the top block, but in terms all of absolute coordinates x rather than relative coordinates r. So if you look at this, there are some guys at x naught, some guys at x1, x2, x3, and then some guys at x1 minus x naught, x2 minus x naught, x3 minus x naught. So this actually has the structure of a 9-dimensional convolution evaluated a particular argument. We integrate x1, x2, x3 out, and each has an offset x0. That's our convolution. Then we finally integrate over x0. So we'll simply use the convolution theorem. We take the Fourier transform of each term. Note that both terms are undisplaced when you take their FTs. You multiply them, and then you do the inverse FT onto the 9D vector x naught, x naught, x naught, a special case of the more general 9D convolution. So first I'm going to focus on the x1 result, and that's all we'll really need. We're also going to assume that the zeta, the 3D 4-point function, is separable with factors denoted by zeta L1 of x1, etc. So for the displaced term, the term on the previous slide that's going to get shifted from the 3D density, we get an integral looking like this. And then for the term from the CMB 4-point basis functions and the delta function, we don't even have an integral. The delta function finishes it for us, so we get a term like that at the bottom. Now multiplying those two terms as the convolution theorem dictates, and linearizing the pair of spherical harmonics we have, and finally defining the x1 integral as just I of k1, we get something like this first line. We have a Gaunt integral script g coupling the L's of the spherical harmonics script L1, capital L1, into a spherical harmonic in big script L1, and then we have our I integral, and we have our j L1 of k1 d star. Now, once we've written this product, we can simply take the inverse transform onto x naught, and I've just shown that result below. The spherical harmonics work really nicely for Fourier transforms. They're always 1-to-1. So y big L1, big M1 of k1 hat goes to the same of x naught hat. Now, the parity of big script L1 is controlled by the Gaunt. It's going to have the same parity as little L1 plus capital L1, because the Gaunt overall makes them be even. We'll get a similar result for the other two integrals for x2 and x3. So now when we integrate over dx naught hat, we are going to need that all the x naught hat harmonics sum to an even number, or the integral will vanish. So just to remind you, this second line I'm showing, starting with the g, I've highlighted the spherical harmonic we get from that. That's big script L1. We'll get a similar thing from our integrals over x2 and x3. So we'll have big script L2 and big script L3 of x naught. And then I've duplicated below the second block here is our original full formula, and I've highlighted in red box the PL naught, which is a spherical harmonic capital L naught of the x naught. So that's where the L naught in this parity formula at the top is coming from. Now, from the Gaunts, we saw that we're going to have little L1 plus big L1 plus script L1 even. Same results for the subscript 2 and 3 L's. And thus we can show that capital L naught plus capital L1 plus capital L2, etc. is going to be even, because we can replace the big script Li's with little li plus capital Li, because that latter quantity has the same parity. So it seems from this analysis like an odd 3D 4-point function can produce an odd CMB 4-point function. In particular, if we look at this last relation here for the parity, we see that little script L1 plus L2 plus L3 will be odd if I had an odd 3D LSS 4-point, and that means that the 4 capital L's sum to an odd number as well, and that means that the CMB 4-point function is odd because those are the 4 L's that determine whether it's odd, so if they're odd, it's odd. However, we haven't looked at the radial part of our problem. The inverse transform for K1, I'm just showing again here, but we need to recall that x naught will go to d star due to the delta function, so this K1 integral actually ends up with 2 spherical Bessels, each with K1 d star. We'll get the same for K2 and K3. We can now ask, what about this I integral, which is just the transform of our model for the 4-point function, the 3D large-scale structure one? So let's assume the simplest 4-point function possible. Let's just assume it's constant out to some maximum radius r and 0 thereafter. This is a good model because our observations go out to some maximum radius r, and we don't know what they do after. We want to ask, is something that's non-zero out to an r allowed? Now, with this simple model of the 3D 4-point function, we can do the integral analytically. So if we choose L1 equals 1, which is going to give you the lowest line parity odd mode, this is what we get at the bottom, just 1 minus j0 of k1r. Now here I'm plotting it, and you can see it's quite sharply peaked at a value of around 1 on the x-axis. That says kr is of order 1. That means we may approximate the integral that we had on the previous slide as sharply peaked in some region of width delta k1 around this value of k1. So doing that, the integral, we finish it, the delta k1 is just the width, and this integral gives us this expression. I'm showing it again at the top of this slide. But now we know that d star over r is much, much greater than 1. So that means that for the k1s where the I is peaked, we're going to be in the asymptotic limit of the two spherical Bessel functions that I've shown above. And in the asymptotic limit, the spherical Bessels have a phase determined by their L. So here, for instance, JL1 of d star over r will have a phase that's determined by L1. Now, for the two spherical Bessel functions in L1 and script L1 to be in phase, we need big L1 and script L1 to have the same parity. Otherwise, the two Bessels will be out of phase and the integral will vanish. So we can conclude that the parity of big L1 is the parity of script L1. Now we can also remember from our earlier work that we had this rule enforced by our integration over dx naught hat. But now using this relationship that the parity of capital L1 is the same as capital script L1, we can plug in the parity of the capital L1 for script L1 and deduce that the parity of L0 plus L1 plus L2 plus L3 is even. Now these are the four momenta that control our CMB 4-point function, and if they're even, then it's even parity. So apologies for a lot of math. I wish I had the whiteboard, but the virtual slideboard will have to do. And the conclusion of this analysis is that the CMB 4-point function must be even, at least for 3D density fluctuations or 4-point function on scales of a few hundred megaparsec, which in that scenario, there's no odd contribution to the CMB. Fundamentally, this stems from the mismatch in the typical large-scale structure scale that we've seemingly observed parity violation on, with the radius of the typical CMB shell of last scattering, 15,000 megaparsecs. This is what was causing the argument of the SBFs to become so large and got us into the asymptotic limit, where we're going to have the same phase of the SBFs. So this analysis means that non-detection of parity violation in the CMB 4-point statistics is totally consistent with the observed BOSS signal. So thank you.